rather than find the behavior of a system as a function of time as we did before, the time domain analysis, we can find the behavior of the system as a function of frequency instead, which we'll call the frequency domain analysis. So we begin by considering a very simple system like we did way back when with resistors, just a variable voltage source and a capacitor, and we want to find the current through the capacitor. Now we're setting it up with a voltage source that goes at a very specific frequency, and so it has the function of time a cosine omega t plus phi, which if we use complex numbers we can say a complex number a with a phase phi, e to the j omega t. And remember, we take the real part of that. Now to find the current through the capacitor we just use its IV characteristic. So the current is C dV dt, and we've said what V is, so we just have to take the derivative of A e to the j omega t, brings down to j omega, and we see that the current is just j omega c times Vt, and so we can then say that the current is just that voltage divided by some resistance-like thing, which we're going to call with the letter Z, and it's going to be a complex number. That complex number is 1 over j omega c for capacitor. So by using complex notation at one particular value of the frequency, we have a current that's still proportional to the voltage in the way we expect, just like with a resistor, except now the proportionality constant, which we've labeled Z, is called impedance rather than resistance, but it still does have the units of ohms. So first definition we have then, the impedance of a capacitor is not constant with frequency, but at a given frequency we have this expression: the impedance of a capacitor is 1 over the capacitance and 1 over j omega. We also know the impedance of a resistor already is just what we knew before. The impedance of a resistor is just R. We can do the same kind of analysis with an inductor rather than a capacitor. Here we have to plug in the integral of V rather than the derivative of V, but with e to the j omega t that's just as easy. We just bring out a factor of 1 over j omega in the denominator this time, and so we get that the current again is proportional to the voltage, but now it's divided by j omega L, and so treating j omega L as the resistance, the impedance, we see that the impedance of the inductor is just going to be j omega L. So if we plot these things in the time domain when we have this frequency, so I have my frequency that I had always, and here I've divided the time so that one cycle takes 2 of these units, and then we see that the capacitance has a phase of 270 degrees or minus 90 degrees because it has a 1 over j in it, and so it's minus 90. It's behind the capacitance and behind the voltage. It lags behind. It's later in time. So and I see that I have a mistake here. This should be IC and this should be IL. And so if here is the peak of the voltage, here's the peak of the voltage, the peak of the capacitance comes a little bit later. The inductor has a phase of 90 because it has a factor of j in it, and so it's a little ahead. So if here is the peak of the voltage, the peak of the inductor happens a little bit early. We can plot all these on the complex plane, so at some given time the voltage has a value like this. It's sweeping around in a circle, and ahead of it is the inductor, and behind it is the capacitance. And so we can plot all those things. So now that we have impedance defined, we can use it just like we used resistance before and do all the kinds of analysis we did before. We can use the node method and the mesh method. We can define Thevenin equivalence and Norton equivalence, and we can do superposition. So before we did the RLC circuit, and it was quite difficult to do in the time domain for a fixed voltage, but now if we do it for a fixed frequency. But now if we do it in the frequency domain using impedance, it becomes almost trivial to solve. So we have our circuit here, and we're just going to add up the voltages going around. So we have the voltage going up, then we have ZR coming down, ZC, ZL, and we have all those times the currents. And so we can just add up the impedances to get the equivalent impedance at the end, and they're just all in series, and they add boom, 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 like that. And so now if we actually write them out at the given frequency, we see that we have the equivalent is, we still have the R, we have 1 over j omega c plus j omega L, and we can pull out the j, and so we have omega L minus 1 over omega c. Remember, 1 over j from here gives a minus sign. And we can find the magnitude of that, which is r squared plus omega L minus 1 over omega c squared under the square root, so that's the magnitude. And the phase is r over the imaginary part. And so we can plot those things. So it's easiest to plot ZR, it's a real number, so it just comes out like this. And then leading it, that is the inductive part. Lagging, that is the capacitive part. And if we add all those three up, we get some equivalent impedance. What will happen sometimes is there'll be some frequency at which the two terms in the denominator vanish, and then we'll get a very small impedance, which will allow a lot of current to flow. And that's what happens in the case of resonance. We can redo our voltage divider using general impedances rather than resistors. So here's the tried and true voltage divider, where I've just replaced resistors with general impedances, and the formula is just the same. It's Z2 over Z1 plus Z2, but now those are complex numbers, and I can make interesting things because of that. If I replace, if I make Z1 a resistor and Z2 a capacitor, then I just plug in here and I'll get a low-pass filter. So let's see what happens. Z2 is a capacitor, so I plug in 1 over j omega c there, and then I plug in the sum on the bottom. Now if I multiply through by j omega c, I have 1 on the top, I have 1 from this term, and then I have j omega rc in the bottom, and you see that when omega is very small, this is 1, but when omega is very large, I have a very small factor getting through, and that's why it passes the low and it doesn't pass the high. If I switch R and C, I can do the same thing. Now I have an R on top. This time I'll still multiply through by j omega C, so I have a j omega RC on the top. I have the same thing on the bottom that I had before, but now when omega is small, this is nearly 0, and when omega is large, these two terms cancel and I get 1, so it's a high pass filter.